Training a neural network can feel like a chain of people passing a message. The first person keeps changing volume and tone, everyone after them struggles. In a deep network, each layer receives its input from the layer before it. When the earlier layer updates, the next layer sees a change distribution. The issue is not that the model cannot learn, it is that each layer keeps adapting to a target that moves while training is happening. Batch normalization, usually called batch norm, adds a stabilizer inside the network. Common pattern is to compute a linear transform, apply batch norm, and then pass the result through an activation function. The exact placement depends on the architecture. First, batch norm looks at the current mini batch. That might be 32 images or 32 chunks of text representations. Computes the average level of the activations in that batch. Are they mostly high, mostly low, or roughly centered? Then it estimates how spread out those activations are. A large spread means the values are scattered. A small spread means they are squeezed together. Each activation subtracts the batch average, I at 1. Intuitively, the whole cloud is moved back towards 0. Next, it divides by the batch spread, so the values do not swing from tiny to huge all the time. The formula on screen may look mathematical, but in words it is simple. Subtract the center, divide by the scale, and add a tiny safety value so division stays stable. Now the next layer receives inputs in a more stable range, so the optimizer does not constantly fight wildly changing activation values. But forcing everything into the same standard shape can remove useful amplitude information. So, batch norm learns 2 extra parameters. One stretches or shrinks the normalized value. The other shifts its center. It is like cleaning the desk first, then putting the important tools back where they belong. Stability does not mean stiffness. Solid second. Key value of batch norm is that internal representations drift less. Later layers do not need to keep relearning the input scale after every update. From the training side, stable numerical scale also helps gradients remain in a usable range during backpropagation. In many classic convolutional networks, batch norm makes training faster and often allows a somewhat larger learning rate. There is also an interesting side effect. Every mini batch estimates slightly different statistics, so training receives a small amount of noise. Sometimes that mild noise acts like a gentle disturbance, pushing the model away from memorizing only the exact training examples. A useful analogy is audio leveling. First, keep the volume from jumping all over the place, then preserve the style with adjustable knobs. There is one important detail. During training, batch norm uses statistics computed from the current mini batch. During inference, the model may receive only one example. Then it cannot rely on fresh batch statistics. The solution is to keep moving averages of the mean and variance during training and use those saved estimates during inference. Batch norm is not magic. The batch is very small. The mean and variance estimates can become noisy. That is one reason many transformer-style models use layer norm more often than batch norm. Roughly speaking, batch norm cares about shared statistics across a batch, while layer norm cares more about the numerical state inside one example. So batch norm is not a magic ingredient that makes a model intelligent. It mainly makes the training environment better conditioned. If you remember one sentence, batch norm measures batch statistics, normalizes activations, then lets the model learn the best scale and shift. Neural networks need a stable mood too, to suppress expression, but to remove chaos so useful changes are easier to learn.